All right, so today I'm going to talk about exponential functions and logarithms. This is in section 1.4. I'm jumping around in the book a little bit. I haven't really finished 1.3 yet, but the stuff that I talk about today is not on this week's homework or this week's quiz. So I am going to jump around a little bit, but by the time you actually have a homework on this stuff, we will have covered everything in the book up until 1.4, so you'll fully know what's going on. But yeah, I just wanted to keep talking about different types of functions. And last time I talked about algebraic functions. This time I'm going to talk about these types of functions. So first, let me do exponential functions, just the basic facts about them. So an exponential function, I mean like a to the x, where a is a number larger than 1. It can also be a number between 0 and 1. We'll talk about those functions eventually, but let's for now focus on when a is larger than 1. And I drew a few examples for different numbers a. Like here in black, we have y equals e to the x. Of course, e is this famous number. It's about 2.7, but it actually goes on forever and doesn't repeat, just like pi. But e is a very common number to be talking about when you're talking about exponential functions, and we'll learn why that is later on. But I also drew, for example, y equals 2 to the x. And of course, 2 is a number that's smaller than e. E is about 2.7, so yeah, 2 is smaller. And when a is smaller, what effect does that have on the graph? Well, okay, you're going to notice that all three of these graphs look roughly the same, at least in the sense that they all go through this point. And as I go to the left, they all have a horizontal asymptote. They're all becoming very flat and approaching this line y equals 0 as I go farther and farther to the right. Of course, some of these graphs are approaching that faster than others, but they're all approaching the same line. And as I go to the right, all of these graphs just go up and up and up. But once again, going back to what effect this number has, the base, that's what this number on the bottom is called. The base, like what effect that has is that if you choose a smaller base, then the part to the right will be lower. Like 2 is smaller than e, and therefore if I look at the right side of the graph, this graph is underneath this graph. And on the left, it's switched. The red graph is above the black graph. Similarly, if I choose a larger base than like 10, in blue we see y equals 10 to the x, this graph is going to, at least for the part on the right, this is going to be above the smaller bases. And on the left, this is going to be below the smaller bases. These functions have a domain of all real numbers. They have a range of 0 to infinity, not including 0. As I go farther and farther to the left, these graphs become very close to 0, but they never cross the 0 line. So the range does not include 0. And these graphs are 1 to 1. They pass the horizontal line test. All right, let's talk about logarithms. That's the other kind. A logarithmic function is what, I'm going to just call it this, like log base a of x, where a is a number that's greater than 1. Again, you can talk about logarithms of other bases, but that's actually really uncommon. Usually when we talk about a logarithm, the base is larger than 1. So similarly, I drew a few graphs of a few different bases, and actually these bases correspond to these exponents, actually, because up here what I drew is 10 to the x, e to the x, and 2 to the x, and down here you'll see log base 10, log base 2, and natural log, which is log base e. So it's the same three numbers. It's 2, e, and 10. So like I was saying, natural log is just log base e, so I drew that here. These graphs have a vertical asymptote at 0, at x equals 0. So they all have roughly the same shape. They come upwards from the vertical asymptote. They all go through this point. This is the point 1, comma 0. That's because the logarithm base anything of 1 is 0. So they all go through the point 1, comma 0. But the effect that the base has is kind of analogous to the effect that the base has up here. It's, you know, if you have a larger base, then to the left of this point, the graph is going to be above the smaller bases, and to the right of that point, the graph is going to be below the smaller bases. These functions have domain of 0 to infinity, not including 0. They have a range of all real numbers, and they are one-to-one. So let me talk about inverse functions. F and g are inverses of each other if, when we do f of g of x, we always get x. Whenever it's in the domain, like x has to be in the domain of g for this to work, but f of g of x should be x as long as x is in the appropriate domain. And also g of f of x has to be x, once again, as long as x is in the appropriate domain for that. So those are inverse functions. And the reason why I'm talking about them is that exponential functions and logarithmic functions, roughly speaking, are inverses of each other. Less roughly speaking, it's if you have an exponential function, then the inverse is the logarithm with the same base. So this is base a and this is base a. And what does that mean? That means if I do f of g of x in this case would be like, so f of x is this, but instead of an x, I put this whole thing. So what I get is a to the log base a of x. And when you see something like that, basically what happens is, and this is, well, so in my head, what I do is I just cross off the a and the log base a, and all that's left is the x. They sort of cancel in that sense. Similarly, if I did it the other way around, instead of doing f of g, I did g of f. So that would mean I look at the formula for g, but instead of an x, what I put is this. I put a to the x. So what I get is log base a of a to the x. And there's a similar cancellation, and you just get x. So that's why, and of course that's why we talk about these types of functions together. Exponentials and logarithms have a lot to do with each other because they're inverses. Since I'm talking about inverses, and since last time I talked about algebraic functions, let me point out that, for example, x cubed and the cube root of x are inverses. And yeah, maybe I won't spend a lot of time checking that, but if I do f of g of x, that would be the cube root of x cubed. And we know the cube root cancels the cube, and we just get x. Similarly, if I did g of f of x, that would be like this with the x cubed on the inside. But we know that doesn't matter. We know we just get x. So these are inverses of each other. And in general, okay, I'm going to give you a caveat. I'm going to have to correct myself a little bit, but in general, a power of x and the corresponding root of x, like a third power and the third root, in general, these are inverses of each other. Let me correct that a bit. If we're talking about x squared or an even power of x and then the corresponding root, then we have to be a bit careful when we call these inverses. Remember, if I do, say, which way do I want to do this? If I do g of f of x, that would be the square root of x squared, which, as we have gone over, is not always x. It's the absolute value of x. If x is a negative number, that's not going to be x. It's going to be the absolute value. So this is why I wrote, if we always assume that x is greater than or equal to 0, so this is like a restricted domain. Here I drew the graph of y equals x squared, but I only drew the part where x is greater than or equal to 0. This function is the inverse of this function. So once again, roughly speaking, a power of x is an inverse of its corresponding root, but if you're talking about an even power, then you have to be careful, and you can only say this if x is greater than or equal to 0. All right, so let's talk about the graphs of functions and their inverses. If I graph a function together with its inverse, so here's an example. F of x, the graph in black, is e to the x. G of x, the graph in red, is natural log x. And what you're going to notice is that these are mirror images of each other, where the mirror is this line. This is the line y equals x. It's just a line that goes through the origin and has a slope of 1. So that's the blue dotted line. And these are mirror images of each other. Similarly, and this is a more complicated picture to look at because it's sort of like going through the mirror. Here's f of x equals x cubed, and g of x equals the cube root of x, which, as we just talked about, these are inverses of each other. And yeah, so I mean, it's not too hard if you, because it's not that bad. It's the only weird part is that, this, like the quote unquote mirror is this line, and these graphs are crossing over it. But they're still mirror images of each other. Okay. Here's some rules for exponents and logarithms. You should know these already. You should really know all of these already, but let me emphasize something. For these logarithm rules, it only works if you only do the, well, you have to obey the domain of logarithm. Like logarithm, the domain is only positive numbers for logarithms. You can only do the logarithm of a number if it's greater than 0. So when I write these rules, this wouldn't make sense unless b and c were greater than 0. And down here, just b has to be greater than 0 because I'm not really doing the logarithm of c. So, but really, all of these rules only make sense if you're doing strictly the logarithm of positive numbers all the time. Okay, so let's do some examples. So here's one, and this is like a common type of problem that you'll see on the homework. Write as a oops, sorry, the instructions are not what I intended. I meant to say expand. So I'm going to expand this, assuming all factors are positive. And when I say assuming all factors are positive, that means this x squared is positive, x minus 1 is positive, x plus 1 is positive. So I can start breaking this down according to the rules. The first thing I notice is that I'm doing the logarithm of a fraction. So I can do, according to this rule, that means I can do the logarithm of the top minus the logarithm of the bottom. Like that. I can still expand because I see multiplication inside of the logarithm. And if I see multiplication inside of the logarithm, I can turn it into the logarithm of one thing plus the logarithm of the other thing. So here I can say log base 2 of x squared plus log base 2 of x minus 1 minus log base 2 of x plus 1, which I just copied down from there. There's one more thing I can do. I see a power in here, and I can use this rule. If I see a power inside the logarithm, I can take that number down in front, and it becomes c times this logarithm. So I can take this 2 down in front. 2 log base 2 of x plus log base 2 of x minus 1 minus log base 2 of x plus 1. And by the way, I'm justified doing all of the steps that I'm doing because we were assuming all of the factors are positive. I'm assuming that x is positive, I'm assuming that this is positive, and that this is positive. Otherwise, this wouldn't make sense. Yeah. So we're going to do another one like that, but let me tell you how to do this faster. If you notice what happened, so here's the thing. There's a way to go straight from this to this in one step. So let me break that down for you. Any factor that's on the top is going to be positive. Let me go ahead and put a plus sign in front of this. It's a little bit silly to put a plus sign because, of course, it's positive if I don't put anything. But let me emphasize, anything that's on the top becomes a positive logarithm. Anything that's on the bottom becomes a negative logarithm, like this one. And any powers come down in front. So let me just go over how to go from this to this in one step. It's going to be several logarithms. They're all going to be base 2. Some of them are going to be positive, some of them are going to be negative. And I'm going to do the logarithm of this, the x, but with a 2 in front, and it's positive because that's on the top. And then I'm going to do an x minus 1. This one doesn't have a power, so I don't put any number in front. And it's positive because this came from the top. And then I'm going to have an x plus 1. This is going to be negative because it was from the bottom, and this didn't have a power on it, so there's no number to put in front. So let's do this in one step. So what are my positive things? My positive things are going to come from the top. Of course, this is natural log. That's just log base e. So when I break this down, everything's going to be natural logs. So I'm going to have, say, a positive 1. So let's do this x cubed. I'm going to write an x with a 3 in the front. Plus, okay, now let's do this. With a 4 in the front, and it's positive again because it came from the top. Okay, now let's do the one from the bottom. It's going to be negative because it's from the bottom. I'm going to write x plus 1, and this one had a power, but the power goes in front. So we did it in one step. There's nothing wrong with taking several steps to do it, like we did it the first time, but there's also nothing wrong with doing it in one step if you can do it right. By the way, it may be tempting to try to do something with this, like I see an x squared, so maybe I want to take this power down in front. I can't do that because what you'll notice is we don't have a rule here to break down log of b plus c. There's nothing in here that tells me how to do the logarithm of parentheses b plus c. Like, yeah, I guess maybe. There's no magic formula that'll convert this into something else for you. You can do b times c or b divided by c or b to the c power, but there's no magic rule for logarithm of b plus c. So the fact that this logarithm has addition in it, that means that I can't really break that addition down. And if I could break that addition down and somehow end up with just this, then I could take this number down. But there's just no way to, there's no formula to really deal with that addition. So we have to leave this as it is. And that's okay. We just call this fully simplified. Okay, so actually maybe I'll cut this video off and make a new one.